Right now, somewhere on Earth, the wind is doing exactly nothing. Not a breeze, not a gust. Perfectly still at least one spot on the entire planet. And I don't mean it happens to be calm there today. I mean it is mathematically impossible for the wind to be blowing everywhere at once. There has to be a dead spot. Always. Every single second of every single day. Nobody has to check the weather to know this. You could turn off every satellite and every sensor and it would still be true, because it's not really a fact about weather. It's a fact about spheres. Some person doing pure geometry, not thinking about air at all, proved that you cannot cover a ball in hair and comb it all flat without leaving at least one cowlick. That's the whole theorem, honestly. It has a slightly ridiculous name. It's called the Hairy Ball Theorem, and I promise I'm not making that up. By the end of this, you'll see why the wind has no choice, and why it's the same reason you have a cowlick on the back of your head. Okay, let's slow down and build this properly because the payoff is worth it. Forget the sphere for a second. Picture a flat sheet of paper, and at every single point on that paper, I glue a little arrow. The arrow can point any direction and be any length. That's it. That's a vector field. It's just a rule that hands you an arrow wherever you stand. Wind is exactly this. Stand anywhere, and the wind gives you a direction and a speed, which is a length. Water flowing in a river, the same. The little hairs on your arm all lying down, same idea. Each hair is an arrow. The one rule I care about is that the field is continuous, meaning if I take one tiny step, the arrow next to me is only slightly different. No sudden flips, no teleporting. Nature mostly works this way. The wind 2 centimeters to your left isn't blasting the opposite direction from the wind at your nose. So when I say wind, just hear a continuous field of arrows. Keep that phrase. It's the whole game. Now here's the thing I got wrong the first time I thought about this. I assumed spheres were special and hard. So let me start one dimension down with something easy so we can feel the difference. Take a circle, just the outline like a rubber band. I want to comb it. At every point I lay an arrow flat along the circle, tangent to it so it's lying down, never poking outward. Can I do that all the way around with no bald spot, no arrow forced to be zero? Yeah, easy. Just point every arrow clockwise. Walk around the loop and each arrow smoothly hands off to the next. And when you come back to start, it lines up perfectly. No stopping point anywhere. The circle combs just fine. So your gut says fine. The sphere is just a fancier circle it should comb too, right? That's exactly the trap. That's what makes the sphere's answer surprising. Hold on to that clean, happy, fully combed circle because the sphere is about to refuse to do the same thing. And the reason why is genuinely strange. Let's be careful about what combing a sphere even means because the rules matter. Picture a beach ball completely covered in hair, or if you want the wind picture, arrows of wind lying along the surface. The key word again is tangent. Each arrow has to lie flat against the ball. It can't point up out of the surface and it can't dig into it. Think about why. Wind moves along the Earth's surface, not straight up into space and not down into the ground. So at the North Pole, the arrow can point toward any city, any longitude, but it has to stay flat, hugging the top of the ball. Same everywhere. Now the challenge. I want to comb every hair flat, everywhere, with no bald spot. A bald spot means a hair with nowhere to point, an arrow of length 0. In wind terms, a bald spot is dead calm. The claim, the whole theorem, is that you cannot do it. Try however you like. There will always be at least one point where the hair just stands up and refuses, or where the wind dies. Let's watch a few honest attempts fail. Attempt 1. Comb everything toward the north, like all the wind blowing up the globe. Looks great over most of the ball. But watch the South Pole. Every arrow is fleeing away from it in all directions at once, so right at the pole. Which way does the hair point? It can't pick. It's yanked every direction equally, so the only consistent answer is 0. Bald spot. And check the North Pole too. Everything crashing inward, also stuck. 2 dead spots. Okay, attempt 2. Get clever. Swirl everything around like the arrows on our happy circle, spinning around the equator. Beautiful along the middle. But the poles are the eyes of the hurricane. The swirl wraps around them. In dead center, there's nothing left to do but stop. Bald spot again. Every trick you try, the bald spot doesn't vanish. It just slides somewhere else on the ball. Like a lump under a rug you keep pushing around and never flattening out. That lump under the rug feeling? That's the theorem trying to tell you something. The bald spot is conserved. You can move it. You can never delete it. So we need a way to catch the bald spot, even when it's hiding. Here's the trick, and it's my favorite part. Take any spot where the arrows aren't 0, draw a tiny loop around it, and walk that loop once counterclockwise. As you walk, watch the arrow underneath you and count how many full turns it spins. Just the arrow's rotation, not your walking. If the field is calm and boring around there, the arrow barely wiggles and comes back where it started. 0 net turns. That's an index of 0, but circle a real dead spot and the arrow does something dramatic. Around a source where everything sprays outward, the arrow spins once as you go around. Index +1. Around a swirl, also +1. Around a saddle, where 2 flows come in and 2 go out, the arrow actually spins backwards once. Index -1. So every dead spot gets a whole number, a little signature. And here's what's beautiful. If a region has no dead spots inside, the total is 0. The index only sees the trouble. It's a way to count the Cowlicks without having to point at them. Now the magic move. It turns out there's a rule about the whole sphere, discovered way before anyone cared about wind. If you add up the indexes of all the dead spots on any smooth surface, you always get the same number, no matter what field you chose. And that number only depends on the shape of the surface itself. For a sphere, that number is 2. 2, not 0. Remember, on the circle, everything summed to 0, which is exactly why the circle could comb perfectly with no dead spots. 0 total means you're allowed to have nothing, but the sphere's total is stuck at 2. And here's the punchline you can feel coming. If the sphere had no dead spots at all, the indexes would add up to 0, but they have to add up to 2. 0 is not 2. Contradiction. So there must be dead spots, and their indexes have to total 2. That gap between 0 and 2 is the entire theorem. The sphere is simply the wrong shape to be 0. But why 2? Where does that specific number come from? This is the part that made me actually put the pen down and grin. That number is the Euler characteristic, and you already met it in school without knowing. Take any way of chopping the sphere into flattish faces, like a soccer ball or a cube inflated round. Count the corners, subtract the edges, add the faces. Vertices minus edges plus faces. For a cube, that's 8 minus 12 plus 6, that's 2. For a soccer ball, do the count, also 2. For a pyramid, 2. It's always 2 for anything shaped like a sphere, no matter how you cut it. That refusal to change is the whole point. It's measuring something the sphere can't shake off. And the wild thing is this counting number, corners and edges and faces, turns out to be the exact same 2 that the wind has to obey. A theorem about polyhedra and a theorem about breezes are secretly the same theorem. That still gets me a little. Here's the test that convinced me the shape is really the thing. If the sphere is doomed because its number is 2, then find a shape whose number is 0, and it should comb perfectly. That shape exists. It's a donut, a torus. Do the corners minus edges plus faces count on a donut, and you get 0 because the hole in the middle eats exactly the right amount, and 0 means allowed. So take a donut and comb every hair flat going around the ring, the long way around, no bald spot. Now comb another donut the short way, through the hole and back, also perfect. You can comb a donut 2 totally different ways with no dead calm anywhere. The wind on a donut planet could blow everywhere forever. So it was never about hair or wind being difficult. A donut and a sphere follow the exact same laws of combing. One is allowed to be calm nowhere. The other is forbidden. The only difference between them is the hole. The hole is doing all the work. Now cash it in for the real Earth. The atmosphere is a thin shell of air wrapped on a sphere, and horizontal wind at each point is a tangent arrow. Continuous, because air doesn't teleport. That's literally our hairy ball. So the theorem lands with no wiggle room. At every instant, there is at least one point on Earth where the horizontal wind speed is 0. Usually it's not one lonely point. It's the calm cores of cyclones and the dead center of high-pressure systems, the places pilots and sailors already have names for. The math doesn't tell you where. It just guarantees the where exists. And notice what we never used. We never used a weather model, never used physics, never used a single measurement. We used the shape of the planet and the word continuous. That's it. The wind obeys geometry. It has no idea it's obeying. Honestly, the first time this clicked, I went and looked at a live wind map just to find the calm spot. And yeah, there it was, sitting in the eye of a storm. Once you have this, you start seeing it everywhere, and it gets funny, your hair. The reason you have a cowlick, that one spot on the back of your head where the hair swirls or sticks up, is not bad luck. Your scalp is close enough to a sphere. Your hair lies mostly flat, and the theorem says flat everywhere is impossible. So a cowlick is not a flaw. It's a mathematical certainty. You were always going to have at least one. Same reason you can't comb a tennis ball's fuzz perfectly smooth. Same reason a spherical magnet can't have a smooth field line tangent all around it. And there's a cousin fact people love. At any moment there are 2 points on Earth, exactly opposite each other, with the same temperature and the same air pressure. Different theorem, same flavor, continuity forcing a coincidence you'd never expect. Geometry keeps sneaking these little guarantees into the physical world, and most people walk around never noticing they're standing inside a proof. So let me leave you with the thing that still bugs me, because it should bug you too. We proved the dead spot has to exist. We proved its index has to add up to 2. But go back and try to make the theorem tell you where the calm point is right now, over, say, the Pacific. It won't. It flatly refuses. It's a proof of existence with zero interest in location. It says something is definitely there, and then shrugs when you ask where. Math does this constantly, and I've never fully made peace with it. Knowing a thing must exist and having no idea where feels like being handed a treasure map that only says yes. And here's the part that really keeps me up. This all worked because Earth is a sphere. 2, not 0. If our planet were a donut, the wind could blow everywhere, forever, and you'd have no cowlick, and pilots would never find a calm eye to aim for. We got the restless planet. The donut people got the peaceful one. Anyway, go find a wind map. The calm spot is out there right now, and nobody, not even the math, can tell you where.